Sure.
Okay, good afternoon. So this is our second day for the vibration analysis training. So we will start with we will finish the part 1 and then tomorrow the part 2 for this vibration analysis. Okay. So vibration analysis, this is our course outline. So you have the art of instrumentation and vibration analysis. So maybe this is the recap for the last webinar, the D1. So
Yeah.
and then the proper for the training for today is about the signature analysis. So you have the signature of the rotating machines. You have the couple unbalance, overhang motor, rotor unbalance, eccentric rotor, angular misalignment, parallel misalignment. You have bench shaft, misalignment bearing, other sources of high axial vibration. So mechanical looseness, A and B. So we have A and B for the mechanical looseness. So we have also B sleeve bearing wear, clearance problem, mechanical looseness C. Then rotor rub, resonance, belt problems A and B, and also C and D for the belt problems. We have also hydraulic and aerodynamic forces. So normally we have many times I encounter this hydraulic and aerodynamic forces in the field during collecting data. So normally if you heard sounds from the pumps or the normally pumps, you can say abnormal sounds. Then if you collect the data, then you can see the signature for the aerodynamic forces and also the bleed fast frequency. So when before when I collect data, then when I see this aerodynamics forces and the bleed past frequency, so I am happy because 100% I can tell to our management that the problem is this one, bleed past frequency. See? But if the problem is 1x, many problems the 1x. You have to analyze, you have to check all the components of the rotating machines. Not like with the wind pass frequency, it's already there, the peak. So we have bit vibration, electrical problems. So electrical problems is you have the two line frequency and then you have side bands. So you have peak on the high frequencies. So it's easy to identify. And then sometimes if there is an electrical problem, automatic the motor will trip. So it's lucky if you can get the vibration reading of the motor that have problem because normally it will trip because if there is a problem with the electric motors and then did not trip, so what happened? The motor will burn. So that's the problem. Okay, so the collision of gear frequencies, gears tooth load, gears tooth wear, gears eccentricity and backlash, gears misalignment, gears crack, broken tooth. So if you have gears crack, broken tooth, when I on my experience, the bearing frequencies is dominant. So you can see only this broken tooth if the if broken tooth already, the motor will trip because it's hard to drive when there is a broken tooth. Okay. So ball rolling bearing frequencies, rolling elements. So stage 1, stage 2, stage 3, stage 4, failure mode. So gears hunting tooth and oil whip is instability. So this course outline for the vibration analysis is very how many? Many more compared to our D1. So the D1 is our basic, but it is very important that we can have the D1 training, because you cannot analyze the problem of the signatures analysis, because if we don't have knowledge for the basic, because all analysis is the foundation is the D1. There are many times that they ask me that they go directly to vibration analysis, but for me, I did not consider. I tell them that no, if you have training for basic vibration, yes, we can go directly with the vibration analysis. But if you have zero knowledge, no, you understand, but it's difficult to absorb the vibration analysis training.
Yeah.
Okay.
Yep.
Okay, the art of bioinstrumentation and vibration analysis. So back to basics, forward to the future. So our objective, the objective of condition monitoring is to provide information that will keep machinery operating longer and the less overall cost. So that's the target of the reliability. So in the maintenance is if they are encounter problem, they will always say stop the machine or shut down the machine. But in reliability, no. That's why we have vibration monitoring, and we have offline and online. The reliability can do that we cannot shut down, but we have to monitor. We have to maximize the equipment, because we have analyzer and line monitoring system. But if your plant is don't have online monitoring system, so that will happen. If the maintenance will say that we shut down the machine, then the machine will be shut down. So it's very bad in the company that they will shut down without knowing what is the problem of the machines. That's
Yeah.
I have experience here in mostly uh, only 80% of power plant don't have online vibration monitoring system. The problem there, the turbine trip, and then what happened? They don't know. They don't know what is the problem.
Yeah.
So what happened? They will call the vendor. They will call a specialist from other country. And then what happened? Uh, how many days shut down? So there's no production. How many losses? Production losses. So if they have online system, just like when I work in Saudi Arabia, we have online system. Then the turbine trip. Then we know what is the problem. Okay, because not all problems are came from the mechanical. Normally,
Yeah.
mostly of the trip came from
Yeah.
operation, miss operation. So sometimes the instrument also. So the instrument, example, the bulb pop up, the bulb pop up.
Yeah.
So what happened to the rotor? The the vibration of the rotor disturbed, so it will trip. Then if you have online monitoring system, then you can say, okay, the turbine trip because of the disturbance of the valve or the operation. Okay, you can run. See, they only shut down for only 2 hours, 3 hours. Unlike if there's no instrument for that one, then they shut down. Okay. Back to basics, you have vibration, simple harmonic motion. You have the oscillation about a reference point, mold, molded, uh, modeled mathematically as x is the as a function of t. Then equals to x sine angular velocity times time or times t. So this is the one in a sine wave. So okay. So normally electrical engineering knows about this one. So that's an advantage when you teach or your student is an electrical engineering. They know the sine wave. Yeah, right? So
Yeah.
you
Yeah.
have the rotation here. Go here. And this is the peak. Zero to peak. And then
Yeah.
this is
Peak.
the RMS. That's why
Yeah.
in our analysis, we always use RMS. So this is the peak to peak.
Mm.
From here to here, that is the peak to peak. Okay.
Yeah.
So this is the one cycle. One cycle.
Yeah.
Okay. So this is the what they call it, the installation of this online, this proximity probe. So this is the rotor. This is the rotor in the machine. So this is the magnetic field. This is the coil, magnetic field. Then coil. Then you have these eddy currents. So this is the proximity probe. This one. This
Yeah.
one. Proximity probe. Then there is a cable. There is a RF, input and output, and then the modulator. Okay. So this one, yeah, we have so in our system one, so we have three kinds of proximity probe. You have the one is the radial, which is 8 volts, 7 to 8 volts. And also radial,
Oh.
we have 3 volts. And
Okay.
then the number 3, we have the axial, we have negative 10 volts. Always negative, negative.
Okay.
Okay. So maybe if you go with the, so you will be assigned in the future for your steam turbine or gas turbine. I'm confusing with your turbine. You have
It's a
gas.
gas turbine.
Gas
Yeah.
turbine. Okay. So because in the previous slides, I always talk steam turbine, steam turbine. So in the future, you can encounter this one in your system one. So
Oh.
make sure that you have 7 to 8 volts, then R
Mm.
3 volts, and then the axial negative 10 volts. You can notice this one that uh, your volts will be in A, out of range. Example, your R configured to only 6 volts or higher, so your R become in A in your system. If
Okay.
you cannot achieve the right voltage, okay, becomes
Yeah.
in A. There's no reading. So
Mm.
make sure that one. Uh, uh, be attentive with that one because time will come
Mm.
if somebody asks you, oh, what happened to your proximity probe in e-reading. So
Yeah.
you can tell them,
Mm.
okay, we can check on the field and we check the voltage
Mm.
if it is
Yeah.
in range or out of range.
Yeah.
Okay, so this one, here's an example. You have the 24 volts, negative 24 volts, right?
Yeah.
Okay, I will draw. I will make a drawing for that one. So I will make this so that maybe in the future you can teach also in your friends So you can tell them what will happen. Okay, this one. Example, this is negative 24 volts. Okay. So the center, example, this is the center line, right? So example is negative 12, the center line.
Yeah.
So,
Z. Yeah.
so when the motor, the rotor runs, so in a sinusoidal, so this one happen.
Yeah. Yeah.
Okay. So this is negative 10, negative 8, negative 14, okay, and so on. So this one. So you got the point. There is the proximity probe here. When it runs, the reading is on this side. Okay? It
Yeah.
you got the point. This one, this one. I discussed it. This
Yeah.
one.
Yeah. Yeah.
So this is the coil. This is the
Coil.
proximity probe. So the center line here in the center line.
Yeah.
So okay. I'm lucky that you are an electrical engineer. So I think you have understand what is the activation or the sine wave for this proximity probe. Okay,
Yeah.
because this is okay. This is radial. If there is a sine wave, this is radial. But the axial is there is no sine wave in the axial probe. Okay,
Oh.
maybe in your exam. Okay, what the question is what probe that there is no sine wave. Okay, so the answer is the axial proximity probe. And the voltage gap
Oh.
is negative 10 volts.
Oh.
Okay. So there's another example that some same peaks values different RMS. So they are same peak. This one the peak,
Yeah.
but different RMS.
Value.
What happened? Because there is some disturbance of the sine wave of the rotor. So okay. So also this one, same RMS, different peak. So what happened here is there is maybe there's a valve open or the pressure during running of the equipment. There's a sudden low pressure, high pressure. Then the vibration go up.
Yeah. Level
One
goes up.
time spikes. This is spikes.
Yeah.
So that's why
Oh.
we did not consider the peak. We always consider the RMS.
Okay.
That's the uh, that's the idea or that's the cause that we always consider the RMS because the peak sometimes there's a small disturbance, the rotor disturb and then there's a spike directly.
Oh.
So okay. So relationship of acceleration, velocity, and displacement. So if you can see in G's, okay, vibration, amplitude, mils, pace, and G's. So displacement from low frequency, in high frequency. The the reading here is go down. So if you go with the high frequencies, the best is the acceleration
Acceleration. Yeah.
because it can reach higher.
Higher frequencies. Yeah.
So the velocity, that's why we use velocity because it is consistent, the velocity.
Yeah.
Yeah. G's, even G's. In your EcoM, your G's is velocity. No, G's. You use
Acceleration.
G's, not
Yeah.
velocity.
G. Yeah.
G's is
Sorry.
acceleration, right?
Yeah, G's is acceleration and millimeter per second is velocity.
Yeah, because I I cannot absorb directly your three axial. That's why I asked you. You have some spectrum. Then I see that this. So
No, no.
hopefully,
In the
ho-
spectrum on the top notch, there is an acceleration uh, and the velocity and displacement. There are three over there.
so
So that's a very hard,
your gist is in velocity, right? Not acceleration.
no acceleration.
Acceleration. Okay.
Yeah.
So hopefully about mobiles, do you use gist or
I think they use
velocity?
all. No, they use all.
Okay, just be careful with the during with your exam because in our
Oh,
exam
yeah.
before we consistent with
Hmm.
the velocity,
Oh,
velocity,
okay.
velocity,
Hmm.
not the gist.
Oh,
Okay,
okay.
yeah, careful,
Yeah.
careful with the units. Okay,
Yeah.
but okay. Uh, in your side now, you use gist because your equipment to collect data is anti-friction bearing, right? No, there's no displacement or no slave bearing.
No, there is no displacement. You're right. Yeah.
That's why you use this. Okay, okay, I understand. That's why you use this because
Yeah.
this is more is good in the high frequencies. The,
Yes, high frequency.
you can see the problem with the
Bearing
bearing.
fault. Yeah.
Okay,
Yeah.
so that's why. Okay, so so this is the picture. We have the from equipment, then cables, signal conditioning, then data acquisition, communication, then remote analysis and diagnostic. This is the online system. This is
Okay.
the online system. So this remote analysis and diagnostic is we can found in the system one. This one, the display.
Hmm.
So here
Yeah.
you can analyze what is the problem. So as you can see here, where's my eyeglass? I can't see. So you can see the bar graph, that X and Y, what you call here, this one.
Yeah.
You can capture the spectrum, the octave,
Mm.
the trend, you can in the system one.
Yeah.
So
Board plan.
also in the EcoIM, you have trend, right?
Yeah. Yeah. Trend. Yeah.
Yeah, okay.
Mm.
That's the important. You can trend, but if you go with the stand alone, there's no trending, so it's hard to analyze. It's hard to decide whether to run the equipment or to shut down. That's
Okay.
the very important with that trending because not all equipment runs smoothly in the start.
Yeah. Mm.
Even example, you have pumps, submersible pump A, submersible pump B. They are the same, but when running, they are not the same
Mm.
vibration.
Yeah.
So
That's right.
just like a queen, right?
Especially the hydraulic pump. Yeah.
Yeah, especially the hydraulic. So that's why we have to train. You have to.
Yeah.
That's why in my previous company,
Mm.
okay, we shut down the equipment and then run. The first time we run, we have to
Mm.
inspect. So if this low
Okay.
vibration, go directly. But if this high vibration,
Oh.
okay, you can start. You can run even high vibration with the limit. So that because
Oh.
you already run and then you shut down. So it's not good.
Mm.
So we have to
Yeah.
monitor the vibration. If the vibration go up,
Okay.
then we have to monitor daily, weekly or daily to monitor that one. If the temperature get high, so that's the problem. But the temperature is steady, then we have to monitor that one. Until such time, the vibration go down. That's the important with the trending. Because if you don't have trending, then maybe you start the equipment and then high vibration, and then you cannot justify, then you shut down again. So it's not good in the plant. So if you are in the reliability, then what kind of reliability? So come back to you. Okay. So this is the offline. So before we have this one I use. So this is when the when we have Saudi decision, then maybe 1 year before I leave. So that's why I go to the site and then I took picture. So this one. So
okay.
So I click data. See this one. This is the
the accelerometer.
But now it's good. Your EOChem, EcoM.
Yeah.
Wireless. Me before this one. There's a cable. And then go to my analyzer. This one, CSI 2130.
Yeah.
See this CSI 2130. I use this one from 2011 to 2017. Then we use CSI 2140. 21.
But CSI is the best one.
Yeah, I cannot compare to those analyzer because I use this one. EOChem, I don't know how it works, but the one I like in the CSI is you can live. You can live, you can analyze, you can manual. What you want, you can. You do not go to the. You cannot go to your computer. You go directly. There's a problem. Example, you can select this from 0 to 100 hertz. You can. Okay, if you suspect there's a problem with the bearing, you can change 0 to 10,000 hertz.
Oh yeah.
CSI. No, that's why I cannot compare. But they said CSI is the best. And also the system one. I cannot also compare about the system one because my system one is GA, Bentley, Nevada. It's also very good.
Bentley, Nevada and the CSI, they are the best in the market.
Yeah, so thank you for me.
These all are the ways.
Thank you for me. I experienced the best.
They are the best. They are the best ones. Yeah.
The best analyzer.
And you're lucky.
Yeah,
you're lucky that you have worked those analyzers.
That's why
we
I
have
am
lots
happy.
of struggle with that EcoM. We have lots of struggle with the EcoM. Yeah.
I read the manual you give to me. I cannot directly how it works. I cannot get it how it works. Maybe if I hands on, maybe I
yeah.
Oh, where is this application? Where is because in CSI many application you can do. Normally in the field manual you can do, and also the software the software you can do trending. Okay, many. That's why during analysis or there's a problem, we can justify easily. We can justify. We have trending. You have all the data. It's not headache because in reliability, if you don't have technical support, it's hard to defend the management. It's very hard. But if you have the technical data, okay. You can tell them, okay, no problem. I tell you this is the problem. Maybe this week it will shut down. Then this is the data, and you did not listen to me. Then it's up to you. See, you can do that.
Yeah.
But if you don't have technical data, that's the problem.
Yeah,
Okay.
that's right.
So this is the one. Then dump to
Yep.
the software. This is the software AMS. AMS machinery. Machinery. Okay. That's the our software. So this one, the software. See, you can have this one, spectrum. You have also the time waveform. You can
Wave.
do anything.
Yep.
You can analyze here, see in the right side.
Yep.
Yeah.
Yep.
You can trend this one. If you want to trend 1 year, you can trend.
Yeah, yeah, we can.
So, but now maybe only memories only. CSI 2140, System 1. That's why I'm happy to share with the one who trusted me also. Because
Yeah,
if
yeah.
somebody don't trust me, but if you trust me, then I can share to you what is my experience, actual experience.
Yeah, that's right.
Okay, I cannot explain totally 100%, but maybe I can inject in your idea maybe 60 to 70, but that is very applicable to your job site or to your plant. It can help you a lot.
Yep.
Okay. So displacement sensors, we have probe, extension cable, and then the driver. How it works, the tip of the probe contains an encapsulated wire coil which radiates the driver's high frequency as magnetic field. So, okay. When a conductive surface comes to close proximity to the probe tip, eddy currents are generated on the target surface, decreasing the magnetic field strength, leading to decrease the driver's DC output. The DC output is usually 200 millivolts per mil or in a similar range. So this one.
Range. We have 100. Yeah.
So this is the activation, this one. After this one, I will give you this slide. And then you can share.
Yep.
You can share to your friends. Okay. We are here for sharing. Yeah, right? And then if you share, yeah, you can also absorb knowledge.
Yep.
Because when you share, that time is, oh, there's a lacking. So that's the time you research because you know what is lacking. So that's another development for yourself. Because if you don't share, then
Yeah.
you're steady, you're stagnant, right?
Yeah.
Okay. So this is the velocity sensors. Hopefully, maybe this year you can go with the system one.
Mm.
So who are the in charge of the system one? Also the reliability, right?
Yep.
Okay, hopefully maybe if you pass the category dito, then maybe they will ask you that you go with the system one. So it's nice in the
Yeah.
system one. Very nice. You can ask me anytime uh,
Mm-hmm.
what do you do or what the points, key points to you should know the system one.
Yeah, definitely. Yeah.
Yeah. So they have acceleration sensors. The pros and cons, measures acceleration, is small size, easily installed to range to 10,000 hertz. Cons is measure acceleration requires integrative to velocity, susceptible to shock and requires power. Okay. Okay. I lost, right? Okay. Machine speed
No.
sensors. We have displacement probes, active or passive magnetic probes, optical permanent, stroboscopes, and laser tag. So, stroboscope. You already buy
Yeah.
stroboscope? The one
What
I
I
told you?
find, the stroboscope is already in the system, in the
Okay.
data analyzer.
Yeah, very good. Yeah. Because what I
But
as
I
what I
never
said to you.
used it.
Hmm?
Yeah, I've never used it. I never
Yeah,
used it.
because the first time I used that one, why does Yap stop running?
Yeah.
So it's nice. It's nice to have that one to check the coupling, especially the coupling when you have problem with
Oh,
the
okay.
coupling. Yeah. Okay. So trending overall. So this one. This is the system one. I have maybe in the first slides. I did the one. I share to you this
Yep.
one, right? This one, the phase change
Yep.
with the critical speed.
Yep.
So the phase 180 degrees. So before in the training, they said that there is a
Mhm.
phase change between when there is a critical speed. So, I tell to myself that hey, it's true that there is a phase change. But when I work in actual, see, you can see the phase change,
Mm.
and this is the critical speed.
Oh, yeah.
So if there is, so take note, if there is a high vibration and there's no changes with the angle, the meaning that is not the critical speed, that is true vibration. So example, this one.
Oh.
Example, okay, this is running speed. Okay. So example, this is running 180 degrees.
Mhm.
180 degrees. Okay. And then the vibration, this vibration, then go high. Okay.
Yep.
Oh, go high. There. Then there's no change in phase angle. So meaning this
Yeah. Yeah.
vibration is true vibration. True
Yeah.
vibration. There is a problem. But here,
Mm.
see, running, then there's a
Mm.
phase change in
Yep.
high vibration, then meaning that is the
High amplitude.
critical.
Yep.
So that's why you must know the critical speed so that maybe your speed here is 100 kilometers per hour, and then the critical speed you must times 2 or times 3 so that you can pass by. Don't stay,
Mm.
example, 100 basic, okay, we go the actual. Maybe the ramp up is 5 meters per second. Then if you pass by the critical speed, you must go higher, maybe 25 meters per second. Because if you steady with the critical speed, the vibration is more becomes more higher. So that's
Okay.
why don't stay with the critical speed. Just directly pass by.
Mm.
Okay. So I hope after your examination, you can experience the system one.
Yeah.
Okay.
Hopefully.
Hopefully. So this is the CSI. So you can actual offline monitoring system. So you can train, see, from you can
Yep.
train from 2011. Yeah, 2011. See?
No,
Then
2012. Yeah.
2012.
Yeah.
Where's my eyeglass? I cannot see.
Mm.
So 2014, this time vibration high. Then we only change the bearing.
Oh,
Change the
yeah.
bearing. Yeah, and then go
Mm.
vibration. Go down. So
Oh.
that's the good in the SI 2140 and the software. We can track the time. So when we go the management, okay, it's here. This time, I tell we can tell them that okay, we will have to schedule for shutdown. We have to change the bearing
Mhm.
because the vibration is very high and uh, the gearbox maybe will be damaged if we did not change the bearing. So, okay.
Oh.
So then they did not see what happened. They did not said that okay, we will shut down. No, but the vibration goes up here. Just the time they
Mm.
said okay, shut down. See,
Yeah.
when we get this vibration reading, we said we shut down immediately because the vibration is very high. So okay, we are safe as an employee. We are safe in our
Mm.
work. That's the
Yeah.
important. If you are collect data on time, see,
Yeah, that's right.
uh, there's a problem before. Okay, I can share to you. Okay,
Mm.
there is A. Okay, compressor A, then compressor B.
Okay.
Okay,
Mm.
so I hope if somebody hear this my sharing, hopefully they will not do this technique, not good technique. Okay.
Yeah, okay.
Okay. When we get the reading, maybe it's only
Mm.
3 velocity overall. Yeah, you take reading overall, right? Overall.
Yeah.
Okay, overall
Mm.
maybe 5 mm per seconds. See,
Good.
because we go
Okay.
velocities. How much is
Okay.
one in G's? In G's. You have
5
direct
millimeter. Sorry?
in G's. In G, this is 5 mm per second velocity because we always use velocity. In G's,
Okay.
how much is
It will
one?
be around
Maybe lower,
maybe,
right?
yeah.
Okay. Now, what happened in the B when somebody take the reading? Okay. When you take the reading,
Mm.
becomes 10 mm per seconds. What happened? Very high, right?
Yeah, very high. Yeah.
Okay. So, what happened? The technique. So, the analyzer, right? So,
Yeah.
he go with the B, right?
Oh,
He select the B,
yeah.
but he take the reading to the A.
Oh, yeah. Yeah.
See. So, what happened? Your B, what is the reading of your B? The same.
10. Oh, the
Okay.
same 5 millimeter. Oh, okay.
Yeah, that's
Oh.
the technique. That's the not good, right?
Yeah, not good.
Okay.
Yeah.
But what happened? What happened? Next day, the next day, the bee burn out.
Oh,
Okay. That is actual. Okay, burn out. Okay. So we check the reading. What is the
okay.
reading of B? Very low.
5.
From
Yeah.
here, the vibration reading very low, right?
Yeah, yeah.
Monthly reading very low. So what happened?
Yeah.
We are safe.
Oh, in
Safe.
that way.
So in our
Yeah.
side, we are safe because. So what happened there? What happened? Oh, the
They,
problem is not vibration. There's another
ah,
problem, right?
okay. Yeah.
So they said, okay, our technician is very good. They get they get collect data on time, but it is not. We have to protect the equipment. We have to
Yeah.
protect that because see, it is true. Burnt out the bee. We are safe because the
Um,
reading is good, consistent. So the management decided, okay, we change the motor because there's another problem that this is not from the mechanical. It is from the wherever comes
Operations.
from.
Ah, ah,
Okay, so but don't if somebody hear this training, so don't do that. You must keep safe your equipment because if the plant will go down or burnt out, maybe whole plant were down. So there are many families are involved, right?
Oh, yeah.
Okay. So this one, analysis and diagnostics. Okay. Yeah, well, technology come to the rescue, remote, centralized, rapid service, power supply problems from. Okay. Okay. So we can start the signature analysis.
Okay.
Okay. So this is the very important because all problems will be based on the signature of the equipment. Okay. So this is amplitude and this is the frequency. Okay. This is 1x, 2x, okay. 2 times bleed pass frequency. Okay. This is a side bands.
Yeah.
Okay. So in the previous, in the D1, we know already how to get the 1x, how to get the 2x, or shaft speed.
Yeah, running
Okay.
speed. Yeah.
Okay. So they are always the same, or one order. What you use? You use 1x, 2x, or order?
We can
In
use
analysis,
both, but I use most of the time 1x.
1x.
Yeah.
Because I have a friend before, he did not do analysis with the 1x or order. No, he go with the CPM, cycles per
Yeah,
minute.
CPM.
Yeah.
Yeah, RPM. Yeah. Yeah.
Yes, he do analysis with the CPM. When I see the computer CPM, why he do CPM? Well, that's his expertise also. So we cannot. For me, I do with the 1x, 2x, but not the CPM. So he good
Oh,
with
you
the
don't do
CPM. So
orders. You don't do
you go also
orders.
order.
No, I don't. I'm asking you normally. Do you go to orders? No.
No. I don't know. Order is the same with the 1x, but I did not. One order, CPM, they are the same, but I did not use that one. I go with the simplicity. Simple. 1x,
Yeah,
2x, 3x.
1x, 2x. Yeah.
So which frequencies exist and what are the relationship to the fundamental exciting frequencies? Okay. What are the amplitudes of its peak? How does the peaks relate to each other? Is there any significant peaks that are their source?
This one.
Okay, so we can find that one in the future slides. So this one, signature analysis. The common question in vibration analysis: what is the shaft speed? Okay,
Running speed.
what is RPM? What is order? So, but
Yeah. Revolution.
they are the same. They
Yeah.
are the same. If you go with the analysis,
Yeah.
okay. Okay, we have the example. Okay, shaft speed is equals to a one-time RPM or equals to one order. They are the same.
Yeah, they are the same.
One-time RPM or 1x. Okay, they are the same. Example, motor speed is 3,600 RPM. What's shaft speed in hertz? So in hertz.
60 hertz.
Okay. So wait, I think this repetition, this one. So what is
Yeah.
the speed in hertz? One time RPM in hertz and
60.
one order in hertz. So they are the
Yeah.
same, right? Yeah,
Same. Yeah.
60 hertz.
Hertz.
Also this one, 60 hertz, right?
Yeah.
And 60 hertz.
Yeah.
So in 1 RPM, 1,800 RPM, the subspeed is 30, right?
30 hertz.
30
Yeah.
hertz, then 30 hertz. So they are the same.
30 hertz. Yeah.
In hertz.
Yeah.
Okay. So this is the competition. Okay. RPM divided by 60. 60 because this is 60 seconds per minute. Then 60 revolutions per second or 60 cycles per second. So cycles per second equals to hertz, right?
Hertz, yeah.
Cycles per second equals to hertz. So that's the example of the question of the category 2.
Yeah.
So, okay. So hertz, they are also the same with the this one. That's 1,800 RPM.
Yeah.
So very simple, right? T divided by 60.
Yeah. Mm.
Signature analysis, you have 1 hertz equal to 1 cycle per seconds.
Mm.
Okay. It is the most common term used in vibration analysis to describe the frequency of the disturbance. So if you don't know the frequency, how to get the frequencies, meaning you are not condition monitoring technician or analyst. Because how you know the problem if you don't know the hertz? Where is the the Cytatia? I cannot know. Where is the problem in hertz? That's the direct terminology. Terminology. Okay. Never forget the cycle per second relationship. Traditional vibration analysis quite often expresses frequency in terms of cycle per minute. See? There's some.
Yeah, CPM.
There's my friend before. He used CPM. But me, when I check his when he analyzed and then I go with his chair and I look at the stuff, cycles per minute. Then I change to velocity. 1x, 2x. Okay. This is because many pieces of process equipment have running speeds related to revolutions per minute. So 60 cycles per minute, 1 CPS, then 1 hertz. So almost the same CPM.
Yeah.
So signature analysis. Okay. I will get my eyeglass because I cannot see the slides. Excuse.
Yeah.
Okay. So this one is, that's why we use velocity. RM is, check this one. RM is velocity in mm per second. See? Okay. Here, so see here in the CSY, CSI 1240, in this right side, we can do anything. This one to for the analysis or diagnostic. Okay. So this one in frequency in hertz. What is velocity in per seconds? Okay. Okay. We change in 1x. So this one, this is. Okay. So we can change 1x. This one in our system 1. And we can also change this to, see, it is easy to know where is the 1x, 2x, 3x, and 4x. And also this one, see, this one, this is 1x, 1x, this is 2x, then this is the 3x. So the frequency here is 59.77. So 59.77 or near to 60 hertz. So the RPM of this motor is 3,600. Okay. That's why we have 1x here. That is the 1x. And this is the 2x. Okay. So here, 1x, 2x, 3x. But in our system one, we can do like this. We can go directly 1x, 2x, 3x. Okay.
Yeah.
So common vibration problem, we have couple unbalance, overhang, eccentric rotor, angular misalignment, parallel misalignment, bend shaft, many more problems.
Mm.
Okay.
Mm.
But actually, in my previous when I work in Saudi Arabia, I did not encounter all of this one because not all equipment have problem with this one. Like this. Maybe after 10 years, maybe because my company is new, so that's why uh, only slick that I have a spectrum. Okay, so this one
Yeah.
problems. Okay, we will start with the single plane unbalance. So
Yeah.
the single plane unbalance, we have 180 degrees phase on the same shaft. One time RPM always present. So one time RPM always present. And normally 2 minutes. So 2 minutes. Amplitude varies with the square of increasing speed. So that's the one of the question. Many times there is an interview. I think maybe when
Mm.
you get interview, they always ask this one. How to know the unbalance? So it is simply this only.
Mm.
Amplitude varies with the square of the increasing speed. So we can do this if your machine is BFD, variable frequency drive, or just like steam turbine, they have 0 RPM to
Mm.
1,600 RPM. So we can notice the unbalance because when the speed is, example, we have speed now is 200, 2,000. If we increase to
Mm.
2,400, then the example is the amplitude, then it will be double. From here, example here is example 5 mm per seconds. Then if you go higher RPM, then the vibration will go times 2 square. So maybe 25
Oh.
mm per seconds. So that's normal. If somebody asks you during interview, how to unbalance,
Mm.
only one time RPM dominant, and then if we increase the speed, then the amplitude will increase also. The amplitude varies with the square
Okay.
of increasing speed. That's the answer. Then you get high. Okay.
So that can be coming 2x also, 3x also.
No, no, no. Unbalance is don't have 3x. In my experience, we have unbalance with the fan. We did not say 1x. I did not see 2x and I did not see 3x with the unbalance.
No, I mean like how you will find that amplitude will varies with the square of increasing speed.
Yeah,
When we
yeah.
can see that.
You can prove that one. Maybe in the previous slide. So me personally, I can prove that there's a fan. We have a problem with the unbalance. Then we shut
Yeah.
down. Okay, we shut down first because the management or the another department, that is not unbalanced. So they change the bearing. Okay, mechanical. They have to fix the mechanical issues. Then we run the same high vibration on X. Then we increase the speed. Then the vibration goes high. So that's the time we balance the fan. So that's my experience.
Oh.
So personally, I can tell you that if there is a unbalance, only 1x. And then the the amplitude varies with the square of increasing speed. That is true with my experience. Okay. So that if somebody asks you, then you can tell them that is true. Or you like to we do this, you have to check. You can tell them, yeah, we have to check. Then we have to monitor the vibration. Then we will increase the speed. If the speed if we increase the speed, then the vibration is still the same. So that is not unbalanced. That is not unbalanced. That's another issues. Okay. So this one, the single plane with 180 degrees in phase. So in phase. This one in phase. Okay. So maybe time will come. You can share to your friend. You can add animation for your slides. So it's still good that there is an animation. Okay. In phase. So single, unbalanced, this one. See? This one, this is a fan. See, this is a yellow.
Yeah.
Yellow. This is the fan. Okay. So that is the unbalance of the fan. Now, in the previous slides, I will when we balance the fan from the GE personnel. So couple unbalance, 180 out of phase. So out of phase. Couple unbalance. So one time RPM always present. Amplitude also varies with the increasing speed. Can cause high axial as well as radial amplitudes. So balancing requires correction into two planes and 180 degrees. So this is the out of phase. So like this. In phase, the same, but out of phase. So that's why there is an axial amplitude, high vibration with the axial. That is out of phase. Okay. So this one, in phase. So the difference.
Yeah.
In phase and out of phase. Okay. See this one. What is this one? Insulator fan. See? In our CSI, 64K21 insulator air fan. Okay, this one, high 1X. Okay. So that's to prove that if there's unbalance, the 1X is very high. Okay, so overhang rotor. So the previous is the unbalance, now is the overhang. Yeah. So in the overhang, one time RPM present in radial and axial direction. So if you get the reading, so the 1X of the radial and the axial is high. So axial readings tend to be in phase, but radial readings might be unsteady. Overhang rotors often both force and couple unbalance. Each of may require correction. So if you have unbalance, you have overhang, this is normally there is high 1X. Normally, high 1X. Yeah. What we did in our overhang, we only monitor. Say, okay, example, when we run this overhang motor, vibration is high. Normally, we get 5 mm to 6 mm or 7 mm per second. That is high.
Okay.
That is high.
Yeah.
but we accepted. What we did is only monitor for couple months. Example, when we run this one weekly, we get first 3 days get reading. They are the same. Then 1 week, the same. 1 month, the same. 2 months, the same. Okay, that's the baseline. Time will come. If there is overhang rotors, then when we say 6 mm diameter, 6 mm per second vibrations, 7, then we said, okay, it's the normal. So that's why when you asked me before that, what is the standard? So you can use the standard. You can use, but we use the actual, the experience in the plant. Because normally this new bearing, okay, new bearing, new equipment, it should be 1 mm per second, right? 2 mm per second. Yeah. New motor, new bearings. That's it. But in overhang, no, it is higher.
Yeah.
Then if you use this standard 1 mm per second or 2 mm per second, then you get the you collect data from the EcoM, then maybe it's yellow, right? Becomes yellow. So yellow.
Yeah.
Oh, problem. See? But you must record that one. You must record. Okay, this is the starting vibration for the overhang. That's the solution. Okay. And then you can see, you know, this 7 mm. If, okay, there's another one thing. 1x, 7 mm or it's 6 mm. But there is no amplitude there. No. Then it's good.
No harmonics, yeah.
Yeah. Okay. But if there is 3 mm low, right? Per seconds, but there is, that's harmonics. The problem. See? You know the different high vibration, 6 mm, no harmonics here, high frequency. Yeah. It's good. Yeah. 3 mm per seconds, low, but there is harmonics here, meaning you have starting
looseness.
Okay, problem with your bearing. See, that's the experience.
Bearing.
So that's why it's good for you that you are an engineer, but you collect data. Me, I am very happy that I experience collecting data up to decision, up to analysis, diagnostic. It's good. It's quite different that you go directly engineer position, then the technician collect data and pass it to you, then you analyze. You can analyze, you can, but it's different that you have feel the vibration in the site. It's good for you. Okay. So that's the, please be only this one. High vibration, but there's a harmonic, well, no problem. So this is the overhang. That's why overhang is always have high vibration. Yeah. Okay. Eccentric rotors, okay. The vibration at 1 time RPM in the direction of the center line of the rotors. So comparative phase readings differ by 0 or 180 degrees. Attempts to a balance will cause decrease the amplitude in one direction and increase may occur in other direction. So if there is a eccentric rotor, this is the this is the
fan speed. Yeah.
We have 1x for the fan and we have 1x for the motor. So in my previous video, I don't have this I don't have the spectrum because we don't have experience like this eccentric rotor.
Now we have this.
You have this one?
Yeah, we have. You get a small before 1x. You get one small spectrum that is belt frequency.
Okay.
So Yeah, you get a small, then that is a
Okay.
belt frequency. And when your 2x is high, that means there is a misalignment between the pulleys.
Yeah, yeah, yeah.
Yeah,
It's good.
you have this
Uh,
kind of things. Yeah.
you can share me the spectrum. Well, I like your spectrum because that is triaxial. Triaxial is it is it
Yeah,
is the
I can share the
yeah.
spectrum. Yeah.
The
Yeah, you can
triaxial
see
is
that
the
there is.
latest model for of the accelerometer. That's why I did not experience I did not experience for the triaxial. That's why I am I'm surprised with it, and I am curious about what is the data or spectrum collected by the triaxial because we use
No,
always before.
I don't think there is much difference. Like, but the concept is the same. Yeah.
Concept is the
So
same. Okay.
yeah.
What we after before is that when we have the management or one of the supervisor
Mm.
uh, yeah proposed for the triaxial, but our superintendent did not accept. So no, no, no. We don't need the triaxial. We use this one three. This is always accelerometer. So that's why I did
Yeah.
not experience. I did not experience the triaxial. Okay, maybe he did not trust for the triaxial. So
Yeah, maybe. Because in ECOM, the displacement is worst. Yeah.
the displacement.
You can't,
Uh,
yeah, displacement you can't, it is really worst. So that in triaxial, we can just get the velocity one is good and the acceleration for your bearings. That's it. Yeah.
okay, okay. So
But
I don't know.
the good thing is like you're saving the time by
Yeah,
not
yeah.
collecting data on all the direction. You're just
Uh,
collecting in one direction and you're getting the data for axial, vertical, and horizontal. So
yeah.
that is the
That's
only thing you're saving time. Yeah.
yeah. The saving time.
And
So
you're, yeah, and you're not, and you're safe also because you're not using the wires, you're just using the wireless accelerometer. So that is
yeah.
also the good thing. Yeah.
So there is advantage. Also, there's a disadvantage, but it's okay. It's up to the management. So, but in the the important is the how to collect the data, how to analyze. Maybe if you go with the you have experience for 2 years, 3 years, then it's good, and then you are confident with the triaxial. Because
Yeah.
if me for me if I work now and then I use triaxial, maybe I cannot decide directly. I have to educate first myself how to deal with the triaxial, right?
Nah. You're thinking too much. Nah. I don't
Oh,
think so. You will have struggle. Nah.
okay.
You won't have struggle at all. Yeah. The
Okay.
concept is the same. Yeah.
Concept is the same.
Just,
Okay, okay.
yeah, yeah.
Okay. Uh, Maybe somebody, oh, you want to work here? Okay, so we have to continue. So yeah, okay. Alignment. Okay. So this is the perfect alignment. So this is the angular misalignment and the pure offset misalignment. Okay. So angular misalignment. So characterized by high axial vibration. So the axial vibration is high. 180 phase change across the coupling. Typically high and 2 times axial vibration. Okay. So not usual for one, 2, or 3 times RPM to dominate. Symptoms could be indicate coupling problems. So okay, this is for the angular misalignment. So that's when the equipment run, okay, that's the movement of the angular misalignment. So the high axial, 1x and 2x axial. Okay. So in the parallel misalignment, so this is the high radial vibration 180 degrees out of phase. Severe conditions give higher harmonics. 2 times RPM, often larger than 1 time RPM. So normally I have many encounter this one in our plant.
Yeah, even
parallel.
Yeah.
Yeah. Not the angular. Angular is not so maybe 2% only for the angular misalignment. But in parallel, many, maybe 30% to 40% problem. Mostly in the plant, the bearing problem. When the equipment runs for 3 years, 4 years, then just the time that there is a bearing problem. Then we change the bearing. That's all. Okay. So this is the parallel misalignment movement. So shaft center lines do not intersect. Note the even high radial axial bearing image. So this is the spectrum, high to X. So I have this spectrum. The 2X is high, see? This is 1X, this 2X, see? Very high.
Yeah.
So the parallel misalignment is when I see this 1 and then 2X high, oh, misaligned directly. And then we have to order work order for the maintenance. And if they can change over the equipment, A and B, then shut down the A, align, and then run the B. That's only.
Do you check the phase also?
The phase?
Yeah, do you check the phase to confirm
No,
the alignment, misalignment?
We don't use we do not check the phase.
Okay.
Okay, we don't. There is a out of phase, in phase, no. We did not use.
Oh.
Okay. So this one, see, you can, in our CSI, we can trend this one. From date before and after. What is the difference?
Oh, before. See? Oh, yeah.
Example, we have weekly, 1 week, and this is the reading, and this is the reading now. See? That is parallel misalignment. That is very good. But the parallel misalignment, if your country is 60 hertz line frequency, and then your RPM here is 3,600, then your 2x, is high, then there's if it is electrical problem or mechanical.
Yeah.
So that's the problem.
With the 2x,
yeah. But your line frequency is 50 hertz. It's easy, right? Yeah. It's easy to identify. It is misaligned or electrical problem.
Yeah.
Because the spectrum here, if it is this is 1x, then 2x, this is 30, then 60. Right? Oh no, this is the 181.
No, if you have a 60 hertz spectrum, and then if you see the same spectrum in 120, then you can say that's an electrical fault.
Okay, if your line frequency is 60, right?
Yeah.
But if your line frequency is 50, example is 60, 180, 120, right? Here.
Yeah.
20, right?
Yeah.
So you can see electrical, this is line frequency, two lines frequency, right?
Yeah, 2 lines frequency.
But if your line frequency is 50, it is only 100.
Then it should be 100. Yeah. Yeah.
So that is two line frequency. Two line frequency, that is 100 hertz.
Yeah.
That's
100
why
hertz.
it's easy to identify the electrical problem when your frequency, your line frequency is 50.
Yeah.
But if your line frequency is 60, the electrical and mechanical have quarrel, because mechanical said that is electrical and electrical said that is mechanical. See, that
Yeah,
is the
that's why we
difference.
have to do the phase analysis.
You do the phase analysis. Okay. Okay. What we did, okay, this is what we did. If there is a 120 hertz frequency, okay.
Yeah.
I think slides here. So that, okay, this one, if there is 120 hertz, okay, what we did is we use the analyzer, we go live.
Yeah.
I think you can do this also to check.
Yeah.
No. You have already, your frequency is 50, so no need for that one.
Oh.
Right? No need.
Yeah.
No need to identify that there is an electrical problem, because in your side, if there is a problem with the electrical, that is automatic 100 hertz. Right?
Yeah.
So now we did this one. We go live with the CSI PT140. We go live. Okay, what happened here? Live. Run the equipment. If this is the vibration, okay? If we stop the equipment, take note.
Yep.
If we stop the equipment, if this vibration will gun directly. Example, if we stop, then the vibration gun. Only this is 2x, 120, this 1x, 60. Then the remaining here, normally this is remaining here, what, 60. The remaining 60 is here, the 120 gun. When you stop.
Yeah.
That is electrical
problem. Okay.
Yeah. But if you stop the equipment and this vibration coincide with RPM, it will go down until stop. Then that is mechanical. Yeah. So that's the technique. If maybe if you encounter there is a 120 hertz and then the line frequency is 60, you have to identify that. That's why I go, okay, electrical and mechanical go in the site. They are quarrel. Oh, there's a problem. Electrical, mechanical. I go with the site. Okay. I go live. Okay.
Yeah.
Come. Okay. Look at the spectrum. Okay. They will watch. Okay. Run. High vibration with the 120. Okay. High vibration. Okay. Stop. When the vibration gone directly. Okay. Electrical problem. Solve. Then another. Okay. I start. Then stop. Then vibration slowly go down. Okay. Mechanical problem. It's aligned. So solve.
Yeah.
That's the technique for the two-line frequency. Okay. So you're lucky in your country. You have 50 hertz line frequency. Okay. So bent shaft. Okay. Bent shaft problems are caused high axial vibration. So axial bent shaft. Cause high vibration. One time RPM dominant if bent near to the shaft center. So careful. One time RPM dominant if the bend is near to the center. Then 2 times RPM dominant if bend is near on the shaft ends. So careful with your to collect spectrum, you collecting data. Okay?
Yeah.
So, okay. If you encounter this one, then so, what we do this one is we have to make run out of the shaft. Okay. If you encounter this spectrum and this spectrum one time or two times, then after shutdown, you talk to the maintenance to run out, to make run out. You know this one, to run out of the shaft?
No, I don't know, sir. What is that?
Okay. So it run out. So example, I have this one. No. Run out this one. I think I have webinar also for the mechanical side. I think you like also to have this topic mechanical. Okay, this one run out. This is a shaft. I cannot. Okay. To know to know the bend. So you
Yeah,
must
yeah.
put
I know
there.
the bit.
You must put here the dial indicator, dial indicator, dial indicator. You can ask your mechanical technician or millwright. The millwright, millwright.
Okay. The fitters. Yeah, yeah.
Yeah, they are good this one about this millwright. The
Oh.
then you turn this shaft. Then the reading here. So the accepted reading here is 0.02 mm.
Oh.
0.02. 0.02. Okay. So that's the run out. So
Okay.
if the problem, they say the pin shaft near to the center, maybe here in the center, maybe in the center. So maybe the run out here is maybe is in 0.1 or 0.2 or above this acceptable limit. So
Okay.
if the run out is near to the shaft ends, so here, shaft ends here, maybe the reading is 0.07 or 0.1, 0.1 mm.
Oh.
Okay, so just to make sure, you ask the millwright
Oh.
if you encounter this problem, bend shaft.
Problem.
Okay. Drink water. Okay. So this is the one. Axial twisting action of the bearing, not axial twisting action of the bearing. Okay. So misalign in the bearings. Okay, we go now misalign in the bearing. So high vibration symptoms are similar to angular misalignment, high axial. So that's why we need, if there's a problem, we have to check daily or 2 days or 3 days, and then we will trend. That's the best. Before we go analyze or before we go the decision, what is the problem of the equipment? Okay, so vibration symptoms similar to angular misalignment, attempts to realign coupling or balance. The rotor will not alleviate the problem, will cause twisting motion with approximately 180 phase. So it's good for you that you do phase, right? If my previous experience before, we did not use this phase analysis. We do not. Okay. 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 So misalignment of bearing normally in the pillow block. So I have training here. If you like, for the shaft proper line alignment, this one should be eliminated. Even you have misaligned bearing, okay, and then we change the bearing because it's damaged. But you you did not correct what is the real problem of the misalignment of bearing. You must align the bearing. So this one, we call this one plumbless unlevel. Plum is unlevel. Level. So if your bearing or pillow block, if there is a pillow block, there is no plumbness unlevel, the problem will always present. The bearing damage now, maybe after 1 month, damage again because you did not correct the plumbness unlevel of this bearing.
Sir, what is pumpless?
Yeah, plumbness unlevel. That is the how to correct the pillow block.
Oh, how to correct the pillow block.
Oh, pillow block. Because the pillow block should be in plumbness. This is the way plumbness. You plumb. You can search in the internet plumbness unlevel.
Okay.
You can search in the YouTube. Then you can see,
Yeah.
this is the one, how to correct plumbness. Because if you did not correct, damage anytime. Okay?
Yeah.
So other sources of high axial vibration, you have bend shafts. So shafts in resonance wear, bearing cock on the shaft, resonance of some component in the axial direction, worn thrust bearing, worn helical or bevel gears, a sleeve
Yeah,
bearing
bevel
motor
gears.
hunting or its magnetic center. This magnetic center, you know, right, for this electrical? You know
Slave
the magnetic
bearing
center?
motor.
No, in
What
the
is
big,
magnetic?
okay, there's no here. So in this one, this is the big motor. Normally,
Okay.
okay, I will tell you. This is a motor, right? This is the
Yeah.
shaft.
Yeah.
This is the flange of the electric motor. There is one here.
Okay.
There's a guide, I think, this one. Maybe you
Oh.
can go, maybe you go this Monday, you can check. There is a line here
Yeah,
in
line
your
here.
shaft.
Yeah, I've seen that. Yeah.
You must check this one when running if your magnetic center is in pointed. This one, this line.
Oh.
That is magnetic
Okay.
center.
Oh.
Magnetic center.
Is it for every motor or only for some certain
Yeah,
kind of motor?
I see that one. A small motor. No, there's no the magnetic center. Okay, this magnetic center is only for the sleeve bearing.
Oh, slip bearing.
Sleeve,
Oh.
when your motor is a sleeve bearing, there is a magnetic center because when the sleeve bearing, it will go drive in to non-drive in, right? It should be
Yeah.
stay on the center.
Ah. So
But the
is it on
anti-friction, if
the
you,
drive end?
the drive in, drive in,
Is it on the
drive in.
drive end? Okay.
Yeah, drive,
Yeah.
drive in.
Hmm.
Look at your big motor sleeve bearing. There is here magnetic center.
Ah.
Okay.
Yeah, I'll
If
see
don't
that.
have,
Yeah.
then you ask for the maintenance or electric host the vendor for this motor to make an indication for the magnetic center. That's very
Oh,
important.
okay.
Magnetic center.
Ah.
Okay? For a sleeve bearing only.
Yeah.
But anti-friction bearing, there's no magnetic center for the sleeve for the anti-friction bearing, because that is fixed already. Fixed. The sleeve bearing, it can move.
Yeah,
Sleeve
it
bearing.
can move.
Yeah, that's why we need to stay in the magnetic center. Okay, so it's good. So that's the magnetic center. So mechanical looseness A. So this one. This one looseness, I have many spectra because that is the when the sleeve bearing got problem already, maybe after 3 years, 4 years in operation, then that's the time there's a looseness of the bearing, mechanical looseness. Okay, so
Yeah.
A, okay, caused by structural looseness of machine fit. The distortion of the base will cause soft problems. Phase analysis will reveal approximately 180 degrees phase shift in the vertical direction between the base plate and components of the machine. So, okay, since you use phase analysis, then you can identify directly for the mechanical looseness on the machine foot, right?
Yeah.
So, see this one? You know this one, this dial indicator.
Oh,
Okay.
yeah.
Sometimes they put auxiliary dial if there is a movement. Then when you go analysis in your face, huh? Face analysis, then you
Yeah, we
can also
use the phase,
yeah,
phase. Yeah.
face
But
analysis.
we don't, I think the dial indicators are used by the fitters.
Hmm? Dial?
Dial indicators are used by the fitters to correct the alignment.
Yeah, yeah. But also it used for the this one if there is a movement or the soft. We use also the dial.
Oh, oh,
So as of now, for the soft, you have two kinds to okay to measurements. For the soft, we use number one dial, and number two we have laser alignment. The
okay.
laser can correct also or can check also the soft of the machine,
Oh, laser alignment. Yeah.
but not running. The equipment is not running.
No, no, not running. Yeah, yeah.
Okay.
That's right.
So here,
But
even it is running.
sorry.
Okay, okay.
Yeah, sorry. But how to differentiate that this 1x is causing not because of the structure or not because of the shaft?
Okay. So, that's why I tell you before, 1X is very complicated. There are many components that 1X, the 1X dominant. So, for us before, we do elimination. Okay. Because you cannot pinpoint directly what is the problem of 1X. So, example, we suspect that is a lost bolt. Then we have
Hmm.
to tight all the bolts. Okay, check. There's also 1X. So one by one, we do to check
Oh,
this 1X. We cannot do directly that is the problem. Not like the unbalanced that if you square the speed, it will go vibration up. No. So
hmm.
this 1X is very tricky.
Yeah.
Okay. So this one, mechanical looseness A. So the base plate looseness of a machine fit. So if you encounter this one, then you correct the base plate first. Then if not,
Yeah.
then another issue, another 1X problem.
Hmm. Oh,
So if your supervisor is not a condition monitoring engineer or not, he is not experienced with this field, then maybe he said to you, oh, why you are not pinpoint directly what is the problem? So maybe you said, he's just silent on him because he don't know. And okay, yes, okay, sir. Oh, I will do it again. But if you manage, me, I'm so lucky because my superintendent is very good in supervision. He is very good. Sir, this happens. Okay. Oh, Francis, do this, do this. See, he is the one who advised that. Okay, okay, do this. Okay, okay, sir, I did this one. Then he is not satisfied. Then okay, do this. See, that's the difference. I like my superintendent. Also my lead before in analysis. So this one A, 1x problem. B, okay. So my mechanical news B is different from A. A is only 1x. 1x.
Yeah.
Balance, foundation, piping. See? Unbalance, foundation, loose bolt, piping. What other 1x?
Resonance, yeah.
There's another 1x is
Resonance.
resonance. Resonance. 1x.
Yes. Yeah. Mm.
See? Mini 1x. And also, this is the only one. That's the problem. But if you have 1x, then have this one. You have 1 up x, and you have 2x, and then 3x.
Looseness.
Then that is mechanical looseness B.
Yeah.
Yeah, so caused by the pillow block bolts. See? Okay. Pillow block bolts can cause 0.5. So if this is 1/2 x, sure, that is looseness. Sometimes caused by crack frame structure or bearing block. So the crack frame is the frame, and also the bearing block. This is the bearing block, pillow block. Okay, so it's easy. You have 1x, 1/2 x.
Yeah.
That is mechanical looseness B. See, I have this one. So this is 1x.
Oh.
And then what is the one? We have
Subsynchronous, yeah.
I have 0.5x, right?
Yeah.
Okay, so it's easy to identify the mechanical looseness B. Yeah. So this one, loose bolt in the pillow block.
Oh.
This is the pillow block.
Yeah.
Okay. So sleeve bearing wear clearance problems. So sleeve bearing. So we have later stages of sleeve bearings where we'll give a large family of harmonics of the running speed. Meaning 1x, 2x, 3x, 4x, 5x, 6x.
4x, 5x.
Yeah, that is the
harmonics.
Sleeve bearing. So this one. 1x, 2x, 3x. Okay. But here, so that's the theory, but in my actual, in the plant, see? Mini. 1x, 2x, 3x. Yeah. So if you see this one, then you can see, oh, this. Me also, I screenshot, then pass to my superior, my engineer, there's an engineer. Sir, looseness. Okay. Work order. Directly. Change the bearing. That's very simple.
But sir, you have, this is pump, right? Then you have blade pass vane also.
Yeah. How much is one? One.
Yeah, you can see
1,
the
2,
blade
3, 4,
pass
5, 6, 7.
7x, yeah.
Here. So this pump, right? Okay. Yeah, I did not see. Okay.
Yeah.
See
so you
water
have
pump.
7. Yeah. So how to differentiate that? I get every time confused with this.
How to differentiate?
Yeah. How to differentiate? Is this a harmonics for the rotating looseness, or this is the harmonics for the pump because of the
No,
blade
okay.
pass
This
vein?
this harmonics of the uh, bearing looseness. This
Yeah. How to
they,
differentiate? Okay.
no, this is not related to bleed plus frequency, bleed pass or bleed bin pass.
Yeah, vein pass.
No,
But
this
you
is
are
not
getting
related.
vein pass, right? 7x.
They are the same bleed pass or vein pass, but this one, no, this is not related to this one. This is problem related to the sleeve bearing.
Yeah,
Sleeve bearing.
how you differentiate, because you have motor and the pump also, and you're getting 7x also.
No, in the bin pass frequency, okay, I have this one. I will give you another slides. Normally,
Mm.
that's why it's good. There is the experience. So normally, if your fan, your pump, normally in a pump you have 5 bins or 5 bleeds. 1, 2, 3,
7, yeah.
4, 5. Example, the 5,
Yeah.
5x high.
Mm.
Okay,
Yeah, high.
you
Yeah.
know, if there is a bin plus frequency, there is a high rise noise floor. You know this one, high rise noise floor. Here in
Oh,
high
yeah.
frequency,
Mm.
or in the low frequency,
Mm.
there is a high rise noise floor. High rise noise floor.
Mm.
Noise floor. That's we consider that the problem is there's a bleed pass frequency.
Ah,
Bleed or
oh,
vein. They are the same.
wind.
Pass.
Mm.
Okay. If there is no like this high rise noise floor here, sometimes here,
Mm.
no, that is not
Mm.
wind pass or wind pass frequency. Because normally if your vein or impeller of your pump disturbed, there is a
Mm.
noise. There is a noise.
Ah,
Okay.
okay.
If your blade or vein or in impeller, again, if disturbed, there is a noise. That's why we have this one.
Mm.
The side bands here, high rise noise floor. Okay.
Oh,
We can do maybe after the next slides. You can see that one.
yeah.
So this spectrum, these spikes is for the looseness only. Looseness.
Mm.
Not consider the wind, blind, bleed pass or wind pass frequency. So this one, see?
Mm.
Okay, see this one. This is I told you this is the rise high rise noise floor,
Noise floor.
right?
Yeah.
Yeah, this one. But this one, this is considered for the looseness, not yet the wind pass frequency. If you see 1x, 2x, 3x after to 10x, you can say to your management, sleep, problem, looseness,
Mm.
and change the
Mm.
bearing. That's it.
Mm.
See this
Oh,
one?
if there is a looseness, if there is a looseness,
Yeah,
so we have to tell them to change the bearing.
yeah,
Mm.
looseness. Your bearing is looseness.
Oh,
You have to
oh,
change
oh,
the
if
bearing.
bearing.
No,
Oh, okay.
okay, this is the scenario. I am also a power plant
Mm.
in power. I am a plant mechanic in power plant, also in the petrochemical. Once
Oh.
your bearing have problem, okay, and
Mm.
then you did not change the bearing, okay,
Mm.
what happened to your example pump? What happened to your pump impeller? It damaged. It will hit the casing because
Oh,
see right. Okay, I will draw. Okay, I will draw. I will draw because it's good to you that you will know what happened if you will not change the bearing. Okay, here. Okay. Example, your bearing. Okay. Example, this is your bearing housing, right? Bearing housing. If you have the center hang pump, this is the shaft. Okay. This is the shaft. Okay. This is your center blade. And this is your housing. Your housing is maybe how much clearance only? Your housing. Okay. Your housing maybe, example lang, 3 mm. No, 5 mm. Clearance. Okay. From here. Did not touch the, say, no touching the impeller to the casing, right? Okay. Now your bearing here is your, okay, is very fit. So maybe clearance here is 0.1 or 0.2 mm. Okay, it depends on the manufacturer. Now, what will happen if your bearing damage here? Okay, damage bearing here. Okay, and then the clearance here is going up. So the clearance here is going to 2 mm. Clearance here 2 mm. What happened now? Your clearance is become 4 mm, right?
4 mm. Yeah.
So it is bearing here to the casing.
Oh yeah.
Right. Then if you did that change, what happened? Maybe the bearing gun. Maybe the clearance here become 2.5. Become 2.5 mm. How much is the total? 5 mm. Oh, what happened to your impeller here? It will touch now the
casing.
Right?
Yeah.
So what happened? If you did not change, your impeller or your blade of your pump touch the casing, then damage. See, that's the real. That's why you change the bearing. Right? You you get what happened.
Yeah.
Okay. So that's why if you have looseness with your bearing, then you must. Okay. So another I input to you. Maybe time will come. Okay.
Yeah.
Okay. You know, in the gas turbine, in your gas turbine, right? The bearing housing. Okay, the bearing housing. Gas turbine. This is the casing. Okay. This is your rotor, right? So, you know, during shutdown or you install new turbine, you must know the diametral clearance. Diametral clearance. Diametral clearance. You put right down. You must know this one. And you know the here, the clearance. Clearance between impeller and the casing. And casing. Here, you must know. Because if the time will come, the bearing got not damaged, but it will be, the babbitt becomes thin. You know the maximum clearance that you must shut down before the impeller of your gas turbine hit the casing. Okay, that's very important. Take note of that in the future. Diametral clearance of your bearing housing and the clearance of your impeller to the casing.
Okay.
See, all sleeve bearing, you must know that one because you must prevent that the impeller will hit the casing. Okay.
Yeah.
It's good. So okay. I think we can finish early because you are good. You understand directly because you have experience. That's the advantage. What I told you,
Mm.
you can figure out and you can imagine, and then you experience in the field how to collect what is 1x, what is 2x, what is axial, what is horizontal. That's good. See?
Mm.
So this is the time waveform of the looseness.
Spike, yeah,
Okay.
impacts.
This is the spectrum of the
Mm.
losses. See, there is high rise noise floor because now it's
Mm.
starting. There's abnormal sounds of the bearing housing already because there is
Mm.
a excessive clearance damage already of the bearing. See this one, damage already.
Mm.
If this one sounds, damage already.
Mm.
So this one, sleeve bearing, see, damage already. See?
Yeah.
You know this one, I am the one who take the reading. This one, take reading. And I also get the temperature. The temperature here is 110 degrees.
Oh,
Yeah.
that's too
110
much.
degrees Celsius. I monitor this one. That's why, okay, sir, when it started with the 90 degrees. 90 degrees Celsius. And
So,
then,
sir, so
okay.
sir, when you put the lubrication also, the temperature didn't come down.
No, no, no. It was already damaged. Even you put, it was, okay. When the bearing damaged already, even you put
Mm.
lubrication, it will not go down. Because already, it, when the shaft and the casing, the sleeve, the bawit bearing and the bearing
Mm.
touches the shaft, the temperature there is rises. You cannot control that anymore. So normally, this kind of bearing, you have 70 degrees, right? 70 to 80 degrees. How much in
Yeah.
your, maybe cold in your side now? Maybe lower? Your temperature,
Yeah,
bearing housing?
lower.
Lower.
Yeah,
Okay.
if it is 60, yeah, it's gone.
Okay. So here, when it started 90 degrees, then I monitor. Then it's okay, the vibration go up. The vibration go up and the temperature go up. Then the result, what is the result? Damage.
Bearing
When
gone.
vibration go up, the vibration is steady. Okay, you must monitor first because it's not 100% mechanical issues. But
Oh,
if vibration go up, temperature go up, okay. Then you did not stop. Then this is happen to your bearing housing. See this one?
mm. Yeah.
Yeah. See that is that's why I'm happy that I have actual experience with this one, and I have also the amplitude, spectrum. I have the picture. Okay, so to make the participants or the student that time will come. Example to you, you are confident to yourself that this will happen. This could be happen.
Mm.
Okay.
Yeah.
So mechanical looseness. Okay. Phase is often unstable. Okay. It's good to you that you have phase analysis. You check the phase angle. It's good. We'll have mini harmonics. Can cause by a loss bearing liner. excessive bearing clearance or loss impeller on the shaft. So the C and the D is almost the same, right? Almost the same spectrum. There is a lot of harmonics. So in
Yeah, a
your
lot of
report,
harmony.
okay, in your report, don't mention mechanical scissor or mechanical D. No, only mechanical looseness. That's it only.
Yeah, yeah, I just put mechanical.
Don't use
Yeah.
a C, E, B, C, D. Only mechanical looseness. It's good. Okay. You have question because I think how many? 1 hour already, right? How many hours now?
We've started 4, 5, 6.
Huh?
We did 2 hours 15 minutes. Yeah.
Okay. So because normally uh, because you already have experience, that's why you are directly continue. There's no question. There's no about the theory, about the competition, because you know already what you input to you. What I input to you is to be you are confident in your job, and in the future exam, you are confident to answer, right? Without any
No,
doubt.
sir, I'm not confident in analyzing.
No, no.
I'm a bit
After
scared.
this one,
Yeah.
you are confident already because I tell you the theory and the actual scenario, the actual
Yeah.
in the plant,
Yeah.
which I have experienced before. So time will come if you encounter these spikes, this spectrum, then you can say, okay, this is what happened. And then when you open the bearing housing, one time only you open the bearing housing, and then your analysis is coincide, then forever. You can say, oh, that's will happen. That okay.
Sir, you don't analyze through sidebands. Don't you use that?
The side bands, yeah, I do,
Yeah,
but
sidebands.
we have uh, we use only because this one we started with the 2011 testing commissioning period. So the first vibration I know already in the plant. That's why we don't do deeper. That is deeper analysis. But as we are the
Ah,
beginners, we are the testing, commissioning, startup, normal operation. I know I know this is the vibration of this pump. I know the history of this pump. Sometimes they are called me, Francis, high vibration in the pump like this. What? Uh, what? Uh, what pump? The seawater pump A. How much vibration like this? Okay, that's normal. So because I have experience. But
yeah.
if you say that at the side bands, I can do that. The side bands, I can do that.
Because
You
our
can
plant is so old, very old, 100 years back old.
100 years. Oh, that's very good experience. Very nice. Yeah.
Yeah, so we have lots of issues. So it's very hard to tell what issue is what. Yeah.
Now, for me, if you tell me like that, it's easy for me. But I don't have the software already. I don't have already
Oh, yeah.
software. If I have the software, then I know also your software. Maybe I can help you, or I can identify the side bands, because the side bands is always there if there is a problem. Normally in the bearing, inner race, outer race, gear
Yeah,
frequencies,
outer
there
race.
is always side
Yeah,
bands,
gay
side
freak.
bands.
Yeah, yeah, yeah.
But that's why I told you in my experience, gear, gearbox. If there
Mm.
is abnormal noise, gear frequencies, only within bearing, then gone. See, we don't need. That's why
Sir,
we don't
you
bearing.
change the bearing of the gearbox, or do
Yeah,
you change the bearing of? Oh, okay, bearing of the
bearing.
gearbox. Okay.
No, okay. That's
Ah,
why gearbox is very hard. It's very hard
yeah, very hard.
to to make crack, to damage very hard. Gearbox, the one who fail first is the bearing. When the gearbox becomes abnormal sounds because there's an impacting, this is misaligned with the bearing, or the impact is not good. Yes, it's true. Because when the I will draw. Okay, so that okay. That's why simple gearbox, right?
Yeah.
Bearing here, all right? Bearing.
Yeah.
Yeah, here only. This is the gear, gear reducer, right? Maybe 3 gears inside.
Yeah.
Yeah. Okay. This is the how shafting. Okay. Now, in new install. Here the bearing is fixed, right?
Yeah.
Yeah. So bearing is fixed, no problem. What happened to your gear miss frequency? Very low.
Increase.
No,
yeah.
it's good. It's good first. Good.
Oh, good. Yeah.
Good. No problem. Okay, good. Gear miss frequency. The impact.
High.
The impact is low, but there's a sounds. Gearbox is always have sounds. There's always sounds.
Yeah.
That the sounds is example. We start this one. Okay. Now, if your bearing have problem, what happened to your bearing? Damage, starting to damage. What happened to your gear miss frequency? Go up.
Increase.
Your sounds here, go up, go up, go up. You know what happened? You know, you cannot get the bearing frequencies. You cannot get.
Yes, that's right.
You cannot get the bearing frequencies. Why? Because the dominant high, the dominant sounds, the dominant sounds came from the gearbox. From here, from the gear. This is very high sounds.
Yeah.
The gear miss frequency very high. So you did not know
bearing frequency.
Okay. So the management, gear miss frequency is problem, impacting, there is a spikes here. Spikes, right? Spikes. Gear miss, gear problem. No, that's not your bearing problem. Bearing damage. Now, as per experience, we have many gearbox in the plant. Which is the bearing? Now, okay, we open the gearbox. Then we inspect the gear. There's no problem with the gear. This is impacting, maybe damage. No. We change the bearing. Run. So, before the vibration very high, the trend. Vibration here. Now, which is the bearing? Go back. So, that's the experience when you have gearbox. Okay. The gear will become abnormal sounds because your bearing fail.
Sir, gear, we have one.
Okay.
We have one equipment.
Okay.
It is a blower.
Blower.
It is
okay.
7 lobe blower. Lobe. You know the lobe blowers?
Yeah, lobe.
Lobe compressors. Lobe.
Okay.
No, lobe compressors. They are lobe they are called blowers. So it is having motor, and then it is having coupling, and the coupling is connected to the again we have a gearbox.
Okay.
And that gearbox have the every time what happened, I told them to do the visual inspection on the gearbox. The gears were good.
Okay.
Very good. Nothing happened. But when after they put all the equipment together, again I got the gear problem.
Okay.
So now what would be my action? Should I have to tell them to change the bearings of the motor or the bearings of the gear?
No, you can. I cannot tell you directly. I want to check first the. I want to see first the spectrum. Spectrum, the bearing housing of your gear,
Sir,
and I
can we
bear
share the screen here? Can
and
we share the
the
screen?
spectrum of your motor.
Yeah, I'll share you the screen. Let's see. Host disabled attendee. Can I share the screen?
Yeah, you can share this one. Okay, share me the vibration of the bearing housing of the gearbox and the vibration of your motor. We will see.
Yeah, sir, to share it, you have to disable. Can you disable that? Mm.
Can
Can you
you can
disable?
share?
I'll show you. Yeah, I can share because I'm using my office laptop. So let's see how it works. Does it work?
You so I will stop share. Then you will share, right?
Yeah,
Yeah, I
I'll
will
see
stop share.
how it works.
Yeah, I will stop share. Okay. Then I will. Okay, I will authorize you to share. Okay, you can share now.
Yeah, just a minute, sir, because we have office different.
Thank you for using Microsoft Sign-in certification. Your sign-in was successfully verified.
The problem there in the gearbox is you must know the gear miss frequency. But if that is old, you don't have the data for that gear, right? Okay.
Hello, are you there,
Hello.
sir?
Okay. You can share.
There? Yep.
You can share
Yeah.
your file.
Yeah. Just a minute. No, I can't see your. Uh, are you online? Hello? Hello? Yeah,
Okay.
sir.
You can
I'll
share. You can
share
share.
it.
Okay. You can
I'll
share your
share
file.
you the screen.
Yeah, share screen.
I'll open this. Can you see my screen, sir?
Yeah, the still blue. Yeah.
Yeah, just a minute. I'll take this up there. Yeah, now I'll do it. So can you see now? Yeah, just a minute. I'll open this.
Yes, I see.
Can
I
you
see my face.
now can you see the one which I've opened it?
Yeah, I see. Okay. What equipment this one?
Yeah, sir, this is our setup, sir. This is our setup. Echo M. Yeah, how it looks, I'm sure sharing you that. Yeah, for example, we have this very worst blowers.
Bugs one, huh?
Just a minute, sir. But you can see my screen, isn't it?
Yeah,
Sir?
yes, I see. Just open.
I
No
thought
problem.
we can't see the screen. But it's good. I can share you what analysis I have to do and all.
Yeah. I also want to see what inside of your software. Okay. I can compare
So
with the CSI. So you can hide this one.
pulse
Hide this.
blower, no. Air blowers east and west. I think this is the one. Yeah, sir. So can you see? Yeah.
You hide this one. The shearing. Hide first. Okay.
Oh, hide it. Yeah. Okay.
Okay.
So can you see now? Yeah.
Yeah. The IC. Okay. The overall vibration.
Yeah.
The
Now, yeah, sir.
okay.
Can you see? This is the one motor,
Okay.
non-drive end. Yeah. So this
Oh,
is the we get, yeah. So there is a lobe compressor and there is a
okay.
gearbox. So every time it shows there is a gear wear
Gear
in
wear.
diagnosis. Yeah.
So
So
in your software, you get directly the diagnosis,
yeah,
right?
we get a diagnosis that there is issue with this, but we can't rely on this actually. Yeah,
Yeah.
because yeah. So sir,
Can you show
do
me
you
the
want me to
spectrum?
open the spectrum? Yeah, which
Yeah.
spectrum you want me to open?
The motor first. Motor. The non-drive.
Horizontal,
The drive.
non-drive, drive end.
Drive.
Yeah, so this is horizontal drive end. This is low spectrum. Yeah, can you see, sir? Yeah, this is the
Yeah.
low spectrum.
So what is this?
This is in acceleration. We can put it in velocity. Yeah.
Yeah. Put in velocity because so this velocity.
Yeah, this is velocity. So triaxial means nothing but it takes acceleration and then velocity. Yeah, that's it.
So where is the radial? Horizontal?
Radial, you mean axial?
No. This is triaxial, right? So where
Horizontal.
is horizontal? This is horizontal.
This is horizontal. Yeah.
So what is the motor speed? Where is the 1x? 60 hertz?
This is 1x.
That
It's 25 hertz. 25 hertz.
So 2 Gs, 2 mm per second. How much is the overall is 2 mm per second?
Yes, this is the highest peak,
How much?
and
I
I'll
think
put the
1 mm.
harmonics. Yeah, this 1x, 2x, 3x, and
Uh,
this is the highest peak. That is, we are getting around 44.59 hertz. One mm, 1 mm per second.
so very low, no problem. You go with the gearbox.
Yeah, gearbox.
Very low. Vibration of the motor is very low. That is anti-friction bearing or slave bearing?
Oh, I don't know that. You mean the motor bearings?
Yeah.
I don't know, sir.
Slave or anti-friction?
I think anti-friction, not slave.
Anti-friction.
Yeah.
Okay.
Yeah.
So you go with the gearbox.
You don't want vertical and axial? You don't want to show that?
No. The vibration is low. No problem with the motor.
Okay. Horizontal?
Yeah,
Gearbox. Yeah.
for the gearbox.
Yeah, this is the gearbox. You want in velocity, is that right? Yeah, this is
So
velocity.
200. You go with the 6,000 hertz.
6,000, yeah.
Yeah,
That
because
means
you have
around
only 200
medium
hertz.
frequency. Yeah, medium frequency. Oh, 6,000 means
See. See that what? 6,000. You have the
yes.
6. How much is your
This is 2,000. Yeah, we have
2,000?
6,000
Yeah,
in 1
6,000.
kilohertz. High frequency.
High
Yeah, this
frequency.
is the high frequency. Yeah.
Okay.
This is high frequencies.
See?
So these
That's
all
the
are
sound.
the gain
See?
mesh.
You have the high rise floor, right? This one.
Yes, sir. This is the high rise. 4. Yeah.
Okay, so
But not much because velocity, we
how
can't
much is
see in
velocity?
velocity. Velocity, because this is high frequency, right? So do
Yeah.
you think we have to see in the velocity because high frequency velocity, is it good in high frequency?
No,
Do
it's
you think
okay. It's the
oh,
gist,
it's
no
okay.
problem. How much
Oh,
is
okay.
the overall?
Overall, yeah. So this is 1.9.
Overall, 1.9 only.
Oh, overall means I have
1.9
to go.
mm per second gist
Yeah, millimeter per second. Sorry.
in gist. How?
In G's, it is two G's.
0.9 gist. 2 gist.
Yeah, zero point 0.9 G's. Yeah.
0.9. So it's low, no? What's the problem? What's you have trend. You have trending for this one? Trend.
Yeah, we have trend. Yeah. Which one you want, sir?
That
Overall
one.
peak to peak one?
That one. That one use the mid MF middle frequency.
Oh, middle frequency.
Yeah. You have to
Middle
trend for
frequency.
how many months you get the data?
We got 1, 2, 3, 4, 5,
You can trend
6.
that one. You can trend that
Yeah,
one.
we can trend that.
Yeah,
We can
trend
do
now.
one. Yes.
Because
Yeah.
if your trending is there's no changes, then there's no problem.
Yeah.
See?
3D, and then we can do it. Yeah. Yeah, sir. Can you see, sir? These are the
Say yes,
trends.
yeah. Okay.
Yeah. See, it's been increased.
Yeah, okay. You
It's
go
been
maximize.
yeah.
See, still how many months?
8 months.
8 months. See, still good.
Oh, still
Still,
good?
yeah,
Oh,
eight
okay.
months is still good. Still good. You can run that, no problem. Still, you have to
Now
monitor
it's
only.
running. Now it's running, but it says in diagnosis, gear wear, there is a
Yes, it's
misalignment,
true.
shock mode,
Yes,
and
it's
there
true.
is
It's true. But
yeah. And
yeah,
it's see, sir, can you see here red dots?
yeah, yeah, yeah,
There is a lot of gear wear, it says.
yeah,
Yeah.
yeah. So
Yeah.
your software, it tells it's true. There is a gear wear, misalignment, because your bearing now is going to fail. But not fail,
Oh,
but not severe.
not severe, but it's
Yes.
going to be fail anytime. Oh.
But not anytime, but still working maybe 2 to 3 months. You know,
Oh.
yeah, okay. You know my trend in my seawater, in my cooling tower, how many years? From 2012, 13, 14, right?
Yeah.
2014, it goes how much? 20 mm per seconds, right?
Yeah, 20, yeah.
So your gearbox is only 2 mm, 3 mm per seconds.
Oh, okay.
Oh, so
But
very
but
very safe.
sir, if you but sir, if you see the time waveform, you can see the time waveform is very high, like 9.85,
Yeah, yeah.
14.5,
Yes, yes, yes.
6.7. Is that
Yeah.
okay? Is
Yes.
that okay to have?
Yes,
Oh,
it's that based on my experience. Based on my experience, it's still okay. We have gearbox before, it runs to 20 mm per seconds, 16 mm per second, 17 mm per seconds. Still okay.
and sir, is that okay to have two G's also? See,
2
here it
Gs.
is two, yeah, this is 2G,
How
and
much
you
in
have
the
two
I don't
2.23G.
no, convert first to the velocity because we always use velocity.
No,
So just
velocity is already here. See, 3.59
okay.
and 2 Gs.
Very low.
Yeah. Yeah.
Based on my experience, also my superintendent is American. Maybe he will
Mm.
laugh. How much? 3
Oh,
mm per second, 4 mm. Run, no problem. See, because we have experience 10, 15, 17, still running. So what you have to do is you must you must tell the operation that the bearing of this gearbox is available on your warehouse.
Okay. Sir, what about this, sir? This is the fan where I did the balancing. And I told you, right, there was a crack on the fan and we did the balancing. And after balancing, it has went to 18.7.
How much before? 24?
Before it was, yeah, because after balancing, it was good. Like it was 1.63 and then it was 1.8, 1.7. And suddenly it has drifted to 2.94. And then it went to 6.9, 5.5, and then it went to 18.7.
18.7? 18.7?
Hello, are you there, sir?
Yes, yes. 18.7?
Hello?
Yeah.
Oh.
Hello?
Hello?
Oh, you are gone. I'm still there.
Hello, sir, are you there?
Yes, I'm here. Hello. It's okay?
Hello, I can't hear you.
You cannot hear me. Okay.
Sir, can you hear me?
Yes, I can hear you. I can hear you. Yeah, I can hear you. No problem.
Sir, I can't hear you.
Okay, it's okay now? You cannot hear me?
I cannot hear you.
Hello, I can hear you. Okay, I can hear you. I can hear you.
Your mic is unmute. Your mic is.
It's okay now? You can hear me?
Yeah, now it's okay. Yeah,
okay.
now I can hear it. Yeah.
Maybe the internet. So, again. Okay. That's the fun?
Yeah, this is the fan, yeah. So if you see this horizontal, I told them that there is a bearing fault because I can't see any unbalance.
This is the waterfall?
Yeah, there is a waterfall. These are the previous trends, yeah.
That is the previous trend.
But I can show you the present one. Yeah, so single one. Yeah, this is the trend. Low frequency.
So this is the low frequency. Oh, very punto Gs or punto mm per seconds? No.
No,
Punto G.
0.2 Gs. Yeah, this is mm per second.
How much is one?
60.
What peak does one?
I don't know what is this. Is this a subsynchronous? Maybe this is subsynchronous peak.
How much is the frequency? What is the frequency?
Of this fan, it is
This one,
24.5 hertz.
That peak.
This peak?
Yeah.
Yeah.
What frequency?
2.25 hertz.
2.25 hertz?
Yeah.
What is the RPM? 2.25 hertz?
No. RPM is 24.5 hertz.
The 1x is 22.5.
Yeah.
This is
24
vertical.
point.
This is
This
vertical.
is horizontal. Horizontal. 24.8 is the rotation speed. Yeah.
28. So the RPM is, how much is the RPM? 28.8.
24.8 means
24.8 times 60. 1488 RPM.
Yeah, yeah.
And then you have 2.25 hertz.
Yeah, 2.25 hertz. 2.25.
That peak is always there or sometimes not there?
No, it's not there. I'm not
That's
seeing in
why.
any trend.
So that's impossible that 2.5 hertz and then 60 mm per second and then low frequency. No.
Yeah, and this is the middle frequency, medium frequency, and yeah,
So
in
very low.
velocity. See, yeah, in velocity it doesn't. So no, brother, no, sir. It is 80. See, can you see here? 80.
Yeah.
Yeah.
What?
1.87 hertz. I think there might be some issue with this. I have to go and check again.
No, there's a there's a sounds. Maybe that is alpha or bravo. Sometimes there's a sounds in the surroundings.
Yeah,
The
yeah, yeah.
accelerometer pick up that sounds.
Okay.
So that's like an skiing. That's not true vibration. The 1.25 hertz. No, it's not.
Oh, so do you think I'll take this again? I don't know why, but it's very wrong.
No,
But if
you
you
can
see,
you check again. Try to check this 1.25 hertz. Maybe it's sometimes there, sometimes not there. So if
oh,
the trend there is sometimes there and sometimes not there, so that is not a true vibration of the equipment.
okay. So, but if you see the 3H,
3 hertz?
3H has, yeah, I mean, drive end of the fan. See, you can see the vibration. It has lot of, see, noise floor. This is the bearing issue.
No. Your okay. Your what do you call this one? Uh, your side scaling. You must scale to 10. This is 5, right?
Yeah, this is 5.
So you scale to 10. 0 to 10.
So you mean there is nothing wrong in
Yeah,
this?
there's nothing there. Still,
Oh,
still good.
oh, still good.
Yeah.
Oh,
See, if
okay.
you scale, because you can see that spikes because your scaling is very low. So you scale that for 10, then it go down.
So, sir,
So
then
that's happened to me.
why this is increasing to 162 Gs peak to peak? If we see the
Increasing
waveform,
122 to
162.
to
This is time waveform.
so how time it change?
Sorry, sir.
The changes, time change from the acceleration.
Oh, acceleration. Yeah. You can see the acceleration is 90 Gs.
90 what 90 Gs.
Yeah, 90
That's
Gs.
why we because I used to do I use my experience as a velocity mm per seconds. We use always mm per seconds, not Gs.
So, so Sir, you never use the time waveform?
No.
And envelope spectrum?
Envelope spectrum?
Yeah. So you never use the envelope spectrum also?
Okay, maybe I use that one. You can reflect what is the envelope spectrum?
Envelope spectrum means it modulates and demodulates the frequencies.
Modulate and demodulate?
Yeah, modulation happens in the envelope spectrum.
No, no, no.
No, okay. Anyway, sir, yeah. So, sir, now you understand, right, how my data looks like this.
Yeah, I understand your data. So
Yeah.
it's very different from the software of the CSI. So
Yes,
here
exactly.
you have the software diagnose directly based on the collected data from the equipment.
Yeah, corrected data.
So in your software, you have many read because sometimes when you take data, there's a bad data. You know, sometimes there's a bad data and good data. So
yeah.
if you get
I'm
the
not
bad
sure
data,
how good that data is, but yeah.
hmm?
I'm not sure how good the data is. I mean, like how data analysis of our is good or not. I am not sure. Yeah, because I don't have experience, right? So I cannot judge that is
Yeah,
good or bad. Yeah.
yeah. But from time to time, your experience will go higher, longer. Then you can you are confident with your decision because if you are a technician and you are also an engineer, so you have to decide. But the decision is good if you have long experience in vibration monitoring.
Yeah.
Okay, and then the software itself, because uh, you know when you have experience. Okay, may example, I use CSI 2140. The number one there is, can I trust your software? Yeah, that's the number one. Okay, how to get data or how it works. So that's another issues.
Yeah.
So for me, I cannot based on your data, I cannot say um, it is good or bad. But based on my experience, your vibration, example for the gearbox, you have only 3 mm per second or 4 mm per second. So with my experience, we go with 15 mm per second, 17 mm per second. So that's the time we change the bearing. So in your side,
Oh,
5 mm, it's still safe.
okay. Yeah.
Yeah.
That's good. I can share the screen so I can
Yeah,
discuss more
you
here.
can call me anytime if okay. If you have if you need help, you can share your files.
Yeah. Yeah.
It's also me. I study with your software. First time I saw that one software. It's quite different. So maybe time to time you can share your files, your spectrum. Then maybe I can internalize that one. Then
Yeah, if I have doubts, that's right.
yeah.
Yeah.
But this one, yeah, 125 hertz. That's not good. Maybe that is frequencies from other other equipment, or from the surrounding, because 1.25 hertz, it's not the mechanical issues. It's not mechanical vibration. Normally, if there is zero point 0.5, that is mechanical. 0.5 hertz, this is rubbing inside. But
Okay.
below 2 hertz, no, there's no like that vibration.
Yeah. Yeah. Maybe some other. Anyhow, I have to go and monitor that again. So I'll monitor it. Because what I find, they have used the wrong lubrication for those bearings. It's an overhung fan,
The
and they
lubrication
have
is what kind of lubrication? Grease, ipito, or
na grease,
fluid? Fluid?
grease, yeah,
Grease?
not fluid, grease.
Not fluid. No, no. Because if there is a wrong grease for
Bearing.
the bearing will damage. There is a high frequencies, not the low frequency.
Yeah, that's this because I believe they have used the wrong grease. When they open the bearing, the grease was cooked.
Plus cook inside.
Yeah, yeah, inside. You can see all the scratches on the bearing, on the
Okay.
frame of the bearing. Yeah, so they have used the wrong grease. They used the electrical grease, not the mechanical ones. And they have
Okay.
not used the high temperature grease. So that is
Okay.
also the reason. Yeah. Then they have changed the grease. Now they say it's good now, but I didn't take the vibration testing. So I'll go and take again. Then I'll know that what is the issue.
Yeah, okay. There's a possibility. That one. Because
Yeah. Yeah.
that's it for electrical, and then you put inside for the mechanical. That's not good. Okay.
Because sir, those two bearings are different bearing. One is the labyrinthine bearing, and other one is the normal ball bearing.
They are different bearing
Yeah, they are different bearings.
for drive-in and non-drive-in. They are
Yeah,
different
yeah,
bearing.
yeah, yeah, yeah. For the non-drive end, they use labyrinthine bearing, and for the drive end, they use normal bearings. Yeah,
Why
because be,
that's the original, or they change it?
because sir, it is very old plant, right? So they have designed the plant by themselves. So I believe there might be issues. There might be issues because it's overhung fan. So the fan is too much weight. So I'm not sure why did they change the bearing. So in your experience, do you give the mechanical people that this bearing is not good for this fan? Do you suggest them something like that?
Hmm, no. Normally for that,
Uh,
normally if you go with the engineering word, if you change what's your bearing in the drive-in should be in the non-drive-in. That's the normal.
nah, they
If
have different bearings.
yeah.
Yeah.
But if there is a special cases, that is a special case, but it needs a trial and error. So maybe that's a time that they have trial and error. It is working or not. So they change again. Trial and error, working or not. Maybe that happened to your equipment.
Yeah, because we have to give the solution also. Like, if this is a bearing, this is failing every time. So what we have to do? Like, should we have to change the
Uh,
bearing and all that?
so you are now condition monitoring at the same time reliability engineer. So you are the one
No,
to
no, I'm not reliability, but they expect that we have to give
yeah.
if we are doing the case study. But yeah, I'm not sure why did they have different bearings on drive and non-drive and yeah.
That's the trading for you because maybe okay if they found you that time will come you will become a reliability engineer, so that's your training ground. You have to collect the data, you have to check the bearing, or you can if you have suggestion what kind of bearing to be replaced, so that's the training for you.
Yeah.
I think that's the training for you.
But it's very
So
hard to concentrate all the things.
yeah, yes. You cannot concentrate. You are condition monitoring, tapo, and then you are the reliability. It's that, but it is a training ground. Then time will come, you become a reliability engineer. Okay.
Nah, I don't want to become, sir. It's good to
Oh.
have condition monitors.
Time will tell. They said time will tell. Okay.
Yeah.
Okay. Still we have oh yeah, many okay. I think 10 slides remaining. Okay.
And then we are finished. Second.
Mm-hmm. Not yet.
If this slide's not yet, right? Yeah. I'm
Yeah.
worried. Oh my
I
God.
have 10 slides remaining. 10 slides.
Oh,
Still okay?
oh, can we continue? Sir, after this 10 slides, is the second round is finished?
Yeah, yes. Tomorrow. The same slide ano. Yeah, 80 slides. Today 80 slides, tomorrow 80 slides.
Oh, yeah, yeah. Okay, okay. Now I got it. Yeah. Sir, can we do tomorrow, please? What? It's already 7.
Tomorrow? Yeah.
Yeah.
We will stop now.
Yeah, yeah, if you don't mind.
Okay, no problem. And then tomorrow we will continue. Okay.
Yeah, tomorrow we'll
Please
continue.
remind rotor rub. We stop the rotor rub.
Yeah, router up.
Okay.
Yeah, thanks, sir.
Tomorrow same
Thank you so.
time.
Sir, are you busy tomorrow?
No, no, no. You can you are available early.
Yeah, yeah, I'm available tomorrow and Monday also.
Okay. Morning. We start morning. No problem.
Morning, yeah. Sir, I'll tell you, sir, because we have long weekend. So maybe my family wants to go outing, but I don't want to go. If they think they want to go, then we have to put the class on Monday. Is that okay? I'll let you know, sir, in the morning.
No,
Yeah. Do
in
you have any
Monday also.
commitments?
Yeah, I have also in my every weekdays. I am also busy with the webinar of my students and the projects.
Oh, okay,
Okay.
okay. Sir, you work every how many Monday? What time you're so much busy? Like you're
No,
busy too much?
I am freelance engineer, so I don't know. Depends. It depends on
Oh,
the client. It depends on
yes,
the
yes.
client.
You have to go to the work also.
Yeah.
Yeah, yeah. No problem,
Depends.
sir. I'll tell you Sunday. Yeah,
Yeah,
so we
Sunday.
can.
Tomorrow, just tell me what time.
Yeah,
Okay.
I'll tell you within. Can I tell you tomorrow morning, sir? Is that okay?
Yes, yes, no problem.
Yeah. How many hours before I have to tell? 1 hour or 2 3 hours
Maybe
before?
2 hours, 2 hours before.
Okay, 2 hours
Okay,
before. I'll
okay.
tell you, sir. Yeah.
Okay, thank you. See you
Sir,
tomorrow.
can you
Okay.
share those can you share those screens today which you have taught me?
Yeah, yes, I can see it here. This video, right?
Yeah, the
Yeah.
slides which you have shared with me, like
Okay, this video and the slides, no problem. I will. Yeah.
yeah. Okay,
Okay.
sir. Thank you so much.
Okay,
You have a
welcome.
great night.
Okay.
Bye.